Welcome to Daemon Automation's Factory Floor AI podcast series.
Today, we're really getting into the weeds, tracing the path from sensor to servo in industrial AI. We're going to dissect the entire technical stack needed for real-time control. Think sensor physics, networks, specialized hardware, right through to the AI models and talking to the actual machinery.
Exactly. Our mission really is to map this whole journey. How do you make AI react instantly in a factory setting? We're looking at how engineers essentially, bend the rules of physics, dealing with latency and bandwidth to make sure a command happens exactly when it needs to. We're talking deadlines under 50 milliseconds.
Yeah.
Hard deadlines.
Okay, yeah, that's fast. Let's frame this with the core problem. Process variable fusion. It sounds complicated, but it's actually pretty intuitive, right?
Yeah.
Like imagine an AI watching a log coming down a conveyor belt towards some kind of loader.
Right.
Visually, that scene looks the same, whether the belt's creeping along or flying, doesn't it?
It does, and that's the crux of it, the image alone. It tells the AI what is there, but not when to act. If that belt is moving at, say, 500 feet per minute, the AI needs to trigger that loader maybe 10 feet before the log gets there. It has to anticipate.
Because the loader itself takes time to move.
Exactly. But if the belt's slow, maybe 50 feet per minute, then the AI has to wait for the perfect spot. Same picture, completely different action needed. The AI has to see the log and feel the belt speed or temperature or whatever else matters. It needs context.
Okay, so speed and context are king. And that means the whole pipeline, from sensor onwards, has got to be incredibly tight. Let's start right at the beginning then, the physical layer, the network. Every millisecond counts here, I imagine.
Yeah.
How do we even define end-to-end latency in this world?
Well, end-to-end latency is basically the total delay. It's everything added up, from the moment the sensor fires through the camera, capturing the image, compressing it, sending it down the wire, the server decompressing it, running the AI, and finally getting the command out.
Wow, okay, so even the camera itself is introducing delay before anything else happens.
Oh yeah, significant delay. Think about a standard camera shooting at 30 frames per second. Each frame takes about 33.3 milliseconds just to capture. And then there's internal processing, maybe some compression inside the camera.
Yeah.
You're often looking at close to 50 milliseconds total delay just inside the camera itself.
We've already hit our hypothetical 50 millisecond hard deadline, and the data hasn't even left the camera.
Pretty much. Which tells you why optimizing every single step is so critical.
So let's talk about getting that data out reliably. Physical connectivity. Why PCIe network cards over, say, a simple USB adapter? Aren't they both just network connections?
Not quite. Stability is the key difference. You absolutely want to avoid consumer-grade stuff here. USB adapters. They often share bandwidth with other devices. They can be flaky, introduce unpredictable delays, jitter.
Jitter being those inconsistent delays.
Exactly. Bad news for real time. Industrial setups use proper PCIe network cards, preferably plugged into slots wired directly to the CPU. That gives you a much more stable, consistent data path. And the cameras themselves often use industrial power over Ethernet, PoE, standards like 802.3a or .3, power and data over one rugged cable, much cleaner.
Okay, solid hardware connection, check. Now what about the software side? The network protocol, PCP versus UDP for sending video streams. What's the trade-off?
Right, this is a classic one. TCP is the reliable one, It guarantees every single packet gets there, in order. If one drops, it stops, waits, retransmits.
Which sounds good, but I guess that stop and wait part is the killer for real time.
That's the jitter problem again. Unpredictable pauses. UDP is different. It's often called fire and forget. It just sends the packets out as fast as possible. No retransmissions, much lower overhead. If you lose a packet, well, you might get a glitch in the video, maybe a dropped frame, an artifact.
But the next packet arrives sooner than it would have with TCP waiting.
Precisely. For many real-time AI control loops, slightly imperfect video arriving consistently fast is better than perfect video arriving with unpredictable delays.
That makes sense. Now, you mentioned getting the command out. That often involves talking to a PLC, right? The programmable logic controller, the factory's brain.
Yep. The rugged industrial computer running the actual equipment. Think Allen Bradley ControlLogix or Compact Logix, those are common ones.
And we saw some notes highlighting how much network distance kills performance when talking to these PLCs.
Oh, it's night and day. If your AI server is on the same local network as the PLC, reading a tag, maybe the current machine status or that belt speed we talked about might take 1 or 2 milliseconds, almost nothing.
Okay.
But try doing that same tag read over a VPN, maybe the server's in the cloud or just a different building. Suddenly you're looking at 100 milliseconds, maybe more.
Wow.
Any hope of fast, closed-loop control, gone. instantly. That local network connection to the PLC is absolutely non-negotiable for high-speed stuff.
Okay, so we've got specialized hardware, maybe UDP for speed, and a super local network. Data arrives at the server fast. Now what? The compute bottleneck. Why GPUs? We hear about powerful server CPUs like AMD EPYC or Threadrippers with tons of cores and huge memory bandwidth, 400, 500 gigabytes per second. Isn't that enough?
It's a different kind of power. Think of that high-end CPU, even an EPYC with 12 memory channels hitting maybe 500 gigabytes is like a handful of brilliant PhDs. They can tackle complex, varied tasks sequentially very quickly. A GPU. It's more like an entire army of soldiers all trained to do one specific thing extremely well and all at the exact same time. It's massively parallel.
And that one specific thing is the math behind AI.
Exactly. Deep learning at the core involves tons and tons of matrix operations, specifically something called general matrix vector multiplications, or GEMV, millions of them for a single inference pass. GPUs, with their thousands of specialized cores, are just built for that kind of parallel math. The rule of thumb generally holds. Even the fastest CPU is usually slower than even a modest GPU for AI inference tasks.
So the bottleneck isn't just raw speed, it's the type of computation and moving the data for it.
Precisely. Memory bandwidth becomes critical. Even with a fast EPYC server, getting data in and out fast enough for those millions of calculations is tough. And for firm, real-time, absolutely must-hit deadlines, you need even more specialized approaches.
Which brings us to that wild EUV photolithography example. Can you quickly explain what that is and why its deadline is so insane?
Sure. EUV, extreme ultraviolet lithography, it's how the absolute cutting-edge computer chips are made. Super precise patterns etched using intense light. The problem: that intense light flash generates heat, a lot of it, very quickly. The silicon wafer itself actually warps just for a moment.
Oh, like a heat haze distorting things.
Kind of, but it's the physical wafer bending. There's an AI model, the wafer heat feed forward or WHFF model, whose only job is to predict that warp and tell the machine how to compensate for it before the next light pulse hits. And it has to do this calculation and send the correction command within 50 milliseconds, flat.
If it's late,
the correction is useless. The wafer is already moved or settled, the pattern gets blurred, the chip is potentially ruined. It's a hard deadline.
50 milliseconds. To meet that, needing something like 195 gigaflops per second per axis. Astronomical compute power. How do they achieve that using GPUs like the NVIDIA P100 or V100? There were three main tricks.
Yeah, three key techniques. First, high bandwidth memory HBM. This isn't your standard RAM stick. HBM is stacks of memory chips placed directly on the same package as the GPU die itself.
So super close, super fast connection.
Exactly. It gives you insane memory bandwidth. We're talking 700, maybe 900 gigabytes per second. Way faster than system RAM. Crucial because those matrix operations are constantly fetching data from memory. They're I/O bound.
Okay, HBM tackles the memory speed on the GPU. What about getting the data to the GPU in the first place? That PCI connection is relatively slow, isn't it?
It is. That's the second trick. Data compression. The PCIe bus connecting the GPU to the rest of the system might top out at, say, 16 gigabits on a good day. That's a bottleneck. So what they do is compress the input data, sometimes by 4x, even 10x, before sending it over PCIe.
Wait, so they spend compute time compressing?
To save time on the slow transfer.
Yeah.
Then the GPU decompresses it incredibly quickly. A P100 could decompress at maybe 33 gigabits, so you effectively more than double the usable bandwidth of that PCIe link by doing this compress transfer decompress dance.
That's clever. Trading compute cycles you have on the GPU for transfer time you don't. Okay, what was the third technique? Something about the math itself.
Mixed precision arithmetic. This is about optimizing the actual calculations. Doing everything in the highest precision, like double precision floating point, is accurate but slow and resource intensive. So they get smart. They perform the bulk of the work, the really heavy multiplications, using faster single precision math. Then, only the parts that absolutely need higher accuracy, like summing up intermediate results where errors can accumulate, are done in double precision.
Tailoring the precision to the specific mathematical step.
Exactly. They even developed custom routines for this, called GPU-MP, that beat the standard libraries like NVIDIA's cubless for this specific task. It squeezed out every last drop of performance, hitting that 198 GFLOPS target.
Incredible. The level of optimization is just staggering. From checking cable types to rewriting the fundamental math operations on the GPU, all for that 50 meters window.
And that same meticulousness applies to the software handling the data before it even hits the AI model, especially with video. Using standard tools like the default CV2.0 video capture in OpenCV for a network camera stream, it often doesn't cut it.
Why not? Just can't handle the network glitches smoothly.
Right. Network jitter, packet loss, it leads to dropped frames, weird visual artifacts like tearing or ghosting. If you feed that messy data to the AI, you get garbage
So
predictions.
how do you fix that? Get a clean stream to the AI.
Two main things. First, use better backend libraries if possible. Things like FFmpeg are often more robust at handling network streams, better buffering, multi-threading. Second, and this is really key for real-time control, explicitly manage the frame buffer. You tell OpenCV, only keep the absolute latest frame, buffer size equals 1.
So if a frame arrives even a tiny bit late, it gets tossed.
Immediately discarded. The inference engine only ever sees the freshest possible image. No processing stale data. That's critical for timing.
Okay, clean data pipeline established. Now for the AI models themselves, we talked about two main approaches, process variable fusion and this trigger camera mode. Let's recap fusion first.
Fusion is that idea of combining sensor types. You take the rich visual data from the camera and you literally just concatenate it, stitch it together with the simpler sensor data belt speed, temperature, pressure, whatever. This combined data package then goes into one big neural network. In the successful cases we saw, they use networks with like 26 million parameters plus.
And the result is an AI that understands the whole picture, not just the visual.
Exactly. Context aware. The reported results were impressive. 95% accuracy even when process speeds changed dramatically and operators had to manually intervene 90% less often. The AI was handling the variations.
Makes sense. Now the second approach, trigger camera mode, sounds almost opposite. Instead of processing more data, it processes less.
Radically less. It's a paradigm shift in efficiency. Instead of the AI constantly watching the video stream, churning through frames, it basically sits idle and waits.
Waits for what?
Waits for a signal from the physical world, a trigger. This usually comes from a simple industrial sensor tied into the PLC. It could be an encoder saying the part is in the exact right position now, or a photo I-beam being broken, or a limit switch being physically pressed, even an operator pushing a button.
So the physical process tells the AI, okay, now is the perfect moment, look now.
Precisely. The PLC gets the trigger signal, tells the AI, grab one frame and process it. You go from processing, say, 30 frames per second, most of which might be slightly off, to processing just one perfect frame, timed exactly right.
The benefits must be huge.
Two big ones. First, accuracy. Because you're inspecting at the perfect moment, you often get 100% inspection accuracy, and the response can be super fast, like 0.1 seconds from trigger to decision. Second, efficiency. You're doing maybe 130th of the processing work compared to continuous analysis. That means a 90% reduction in compute needed. You can potentially use much cheaper, less powerful GPUs, or handle many more inspection points with the same hardware.
That's really clever. Okay, we've covered the journey, network, compute, AI models. But we need to close the loop. Commanding the equipment via the PLC. How fast does that final command need to happen?
Yeah, the final step. The AI makes its decision. Now it needs to tell the PLC what to do. Generally, for tight control, you need that communication, reading PLC status, and writing commands back to happen in the 1 to 10 millisecond range.
Back to those super low latencies again.
Always. The AI's output, maybe a complex prediction, gets boiled down to something simple the PLC understands, turn this output on, set this value, etc. And again, PLCs, like those Allen Bradley units, typically use protocols like CIP, often over TCP port 44818 on that crucial local network.
So it all comes back to that. Every optimization from the HBM memory on the GPU down to the OpenCV buffer setting, it's all in service of getting that final command to the PLC within, say, 10 milliseconds of the decision being made.
That's the driving force behind the whole architecture design. You'll see system docs always have sections on PLC integration setup and defining the PLC packet structures. Every choice network card, compression, model architecture, trigger mode is evaluated against that final requirement. Can we reliably get the command to the PLC while it's still relevant to the fast-moving physical process?
It really highlights how much engineering goes into essentially fighting against the speed of light and processing delays, doesn't it?
Yeah.
Starting with worrying about milliseconds in a camera, ending with custom math on $1,000 GPUs.
It's intense. But what's really interesting is that we now have proof points, like that EUV example, showing that these incredibly tight sub-50 millisecond control loops are achievable for really complex tasks. It takes specialized hardware, clever software, mixed precision math, the whole toolkit.
So the capability is there. We've demonstrated AI can process sensor data, fuse it with context, and time physical actions with millisecond precision. Thinking ahead then, what processes out there, maybe things currently needing a skilled human because they seem too fast, too complex, too variable for automation, what's now potentially on the table for this kind of perfectly timed, context-aware AI control? That feels like the next big wave in manufacturing.
This is what intelligent automation looks like. To learn more, visit daemonautomation.com.